All right. So now, with regard to some terminology, I wanted to just kind of go over a few important concepts that we have in thermodynamics just real quickly. A couple of important things that we're going to need to know as we go forward, okay? And basically what we're trying to do today is just kind of cover that first chapter, kind of cover most of that stuff, and you do have a homework due next week that's kind of centered on that first chapter. One very, very important distinction in thermodynamics is going to be the difference between a closed system and a control volume. Okay? So let me first describe a closed system. It could be something like a box, like this. Okay? I like the example of, consider a can of pop or something like that. Okay? Consider something like that. Okay? A closed system is kind of like a pop can that you haven't opened. Okay? There is no mass transfer. No mass can go in or out of a closed system. Okay? No mass can go in or out of a closed system. But that doesn't mean there's no energy transfer. You can still have energy going in or out of a closed system. Yeah. For instance, use the pop can analogy. Let's say I go downstairs and I get a can of pop. It's likely coming out of the machine cold. If I take this can of pop, I put it here on the table, and I come back 24 hours later, it's probably going to be a lot warmer, right? If I come back 24 hours later and I open it up, it's probably going to be room temperature, okay? Now, that's a closed system. There was no mass transfer. I mean, if that pop can is still closed when I come back 24 hours later, it's a closed system. But there was energy transfer, right? Because there was heat from the room transferred in to warm up the pop can, right? There's energy transfer, okay? So you can still have an energy transfer in a closed system. There's just no mass going in or out. It's all inside, okay? But there still is energy transfer in a closed system, okay? So no mass can go in or out of a closed system, but you still have energy transfer. That is a closed system. We're going to be dealing a lot with closed systems, especially the first 5-6 weeks of the course. Closed systems tend to be a little bit easier to deal with than control volumes, open systems. Okay, and so we're going to start there, kind of get our stuff going there, and analyze closed systems. But most of the world isn't like that. Most of the world has systems that are coming in and out and have mass transfer and all sorts of stuff. And so then we have a control volume. Now a control volume may look something like this. Maybe it's like a tube or something like that, and you have got mass that can flow in, and you can have mass that can flow out of that. And and of course you can still have energy. Energy can still flow in or out as well. A true control volume then is not anything more than an arbitrary boundary that we put into practice. What I'm drawing for you there in green is an arbitrary boundary for our control volume. That's what we're going to analyze when we get to control volumes. It will be an arbitrary boundary. Why I say the word arbitrary, because if I were to show you a system, you couldn't see the control volume. You couldn't see the boundary. It's just in your mind. There's nothing real about it. It's just we draw a boundary. We say, okay, this is the volume I'm going to study. Yes, there's stuff going in, there's stuff coming out, there might be energy transfers, there might be all sorts of stuff going on, but I'm going to analyze just this volume. That's a control volume. Okay? And so that's going to be an important concept as we go on. You have mass flowing in, mass flowing out, you got the whole thing. Okay? That's a control volume. But for the first 5 or 6 weeks, we're going to mainly focus on the closed system. Okay, not that you will never see a control volume, but mostly we'll see more closed systems. So there won't be mass flow. That makes it easier. That's going to make it a lot easier. And we get to the control volumes. Okay? I think you all can see the distinction there. So it is an important distinction to recognize because the way we approach the problem, whether we model it as a closed system or we model it as a control volume, the way we approach either one is going to be important. Okay? All right. A couple more concepts and we'll be done. State of a system. Okay. The state of a system is also a very important concept. It basically is a set of properties that completely define a system. A set of properties that completely define a system. Now, you might say, well, what are properties? Properties are physical characteristics of a system. Physical characteristics of a system. Now, what kind of physical characteristics might there be? Well, very simple things like temperature, pressure, specific volume. There's lots of them. There's other ones too. We'll get into them later. Okay? The things that define a system. So, for instance, the pop can. What kind of properties might be of the can of pop when I get it out of the machine? Well, the can of pop probably has a temperature maybe of 35 degrees Fahrenheit. The internal pressure inside the can is a little bit greater, right, than atmospheric pressure. I don't know what it is, but it's you know, I'll make up a number. It's 20 psi. I don't know. But it's greater than outside, right? Because you open up the pop can, it releases pressure, right? So there's a certain temperature, there's a certain pressure, there'd be a certain specific volume of the fluid, okay? Things like that, okay? There's other properties too. We'll get to them as we go. Here's the point I kind of want to kind of get you to, and this is the reason I brought this up. Notice I brought a little chart there. It has an x-axis and a y-axis, okay? When we know the state of a system, that means we know everything about that system. It turns out that we need two independent properties to find the state of a system. Okay? You need two things. What that practically means is if I want to figure out all the stuff I want about that system, let's say that can of pop, if I know two things, maybe the temperature, pressure, other things, if I know two things, I usually can figure out all the other properties of the system because I've defined the state. And that's the beautiful thing we're going to do a lot of. We're going to figure out what are the two properties we can figure out of that system, and then we can figure out the state and get all the other properties that I need. And I draw this chart because it's kind of analogous to, let's say I want this coordinate point right here. Okay, I want that coordinate point. It's not good enough to say, well, that point is at a value of x equals 8. It's not good enough to say that point is at a value of y equals 9. You have to have both the x and y coordinates, right, to find where that point is. It's just an analogy. You have to have two independent properties to define the state of a system. I bring that up now just to get you kind of going so that every week we keep talking to this. By about week 5 or 6, you get it. And you go, oh, I need two things, I need two things, I need two things. You'll get it. Right now, I know you don't get it. You're kind of like, okay, he's telling me I need two things. Whatever. I'll just move on. But later on, that'll be very important. Okay? So I'm kind of just planning that right now. The state is the whole set of properties. Properties are things like temperature, pressure, specific volume. There's lots of other ones. We'll get into them. And you need two of them to get all the other properties. There's like 10 or 15 properties that we're going to use a lot of. But you need two to find the others. Okay? All right. Lastly, real quick, processes and cycles. This is a very simple concept. A process. Process is anything that changes a system from one state to another. Okay? So basically anything that changes the system properties is a process. So for instance, when I put that can of pop and it was cold, and then I waited 24 hours and now the pop is warm, that 24 hours can be thought of as a process. The 24-hour process changed the pop from being cold to warm. Okay? Anything that changes something is a process. Okay? We're going to deal with a lot of processes. And lastly is a cycle. We deal with a lot of cycles too. That is a series of processes that return the system to the original state. It's not a cycle unless you bring it back to where you started. You have to bring it back to where you started. It's a series of processes that return the system to the original state. You may have heard of an engine cycle, a cyclic engine. We're going to study that. We're going to study that cycle in an engine. Okay? Refrigeration is a cycle. Okay? There's a lot of important cycles. Power plants run on a cycle. Okay? It's all cycles. Okay.